One last method. This method now is very similar to the one we've seen before, except for one major difference. So we're still going to rotate this region, but this time we're going to rotate it around the vertical axis, and just to keep things simple, we're going to keep the vertical axis outside the region. Okay, so we want something which is, something that is not inside. So it could be outside, it could be at the edge, but the important thing is that the axis of rotation does not cut through the region. Otherwise, we have to be very careful in how we set things up. Alright, so in this situation, we may want to draw our slices horizontally, but that pretty much means switching x and y and setting up the whole integral in terms of y and so on. Your textbook actually may talk about that, just like many other textbooks do, but I do not recommend that we go there. If that is the way you want to do it, you might as well just switch the variables x and y and just work with a horizontal axis instead. But there are some situations where that switching of x and y does not really work. It does not create anything easy. In fact, it creates something complicated. So in that situation, what we're going to do is we're still going to draw our slice, okay, to compute our volume. So we're still going to draw our slice in the usual way, but this time we're going to rotate that slice around our axis of rotation. This time I'm labeling the height of that rectangle as h, and you're going to see in a second why. It's not going to be r, because remember, now we're rotating around the vertical axis. So again, use your imagination to figure out what happens when I rotate that slice around that vertical axis. Did you get it? Well, this is the best I could come up with graphically. Okay, so when I approximate, I get something like this, right? Is that the same thing that you had in mind? Well, hopefully similar. This is what we call a cylindrical shell, and what it is, it's really just a big cylinder with again a small cylinder drilled in it. It's pretty much the same as we had before, except that now the thickness of the cylinder is pretty big in terms of the height. So the height of the cylinder, that in the previous case, in the case of discs and washers, was delta x, now has become a big quantity h, while in fact the difference between the outside and the inside the cylinders, which before could be very big, has now become a very small amount. In fact, it's our delta x. So as we compute the volume of this cylinder, what we have to do is we have to consider both the outside radius, we have to consider both the radius of the cylinder, and remember, since we're talking about infinitesimally thin strips, we don't have to worry too much about the outside and the inside. We can think of sort of the average radius. So we use that radius there to construct the volume of this cylinder. So it's going to be 2 pi r, which is the volume, the area of the base of the circle, times the height. If you think about it, 2 pi r is the circumference of that cylinder times the height h. It gives us the area of the lateral area of the cylinder, right? So to get the volume, now I have to multiply that by the thickness of that cylindrical shell, which is delta x. Now, if you're not convinced that that is totally correct, because after all, I'm multiplying 2 pi r h, which is just well, what is it, the inside, the outside, the middle circumference of that shell, not quite clear. You can go through all the moves, and it's a great exercise for you to do by actually differentiating the outside radius of that cylindrical shell, the big one, and the inside radius, the one at the hole, which is slightly smaller. Call them two different radii, just like we did for the washers method, big R and little r, and then go through the steps, and you'll see you come up with exactly with the same formula. Alright, so after we've done that, the next two steps are actually the usual ones. So we're going to add up and take the limit, and what do we come up with? Once again, a Riemann integral. And what does it look like in this case? Well, it's going to be the integral from a to b. Now we have 2 pi being the constant that can come out of the integral, and on the inside we're left with rh dx. Now notice that here, as well as in the other two examples of discs and washers, the radii, or in this case the radius and the height, are both left unspecified. That's because they're going to be different functions of x depending on what region you're rotating and around which axis of rotation. So as we go through the formulas, through the examples, we'll see in class many situations where the radius or the radii in the case of the washer and the height of the cylinder are going to be described by different formula. In each case, we'll have to develop what those formula are geometrically, just by looking at the picture and figuring out geometrically what those quantities quantities are, which means that it's going to be very important for you to actually sketch a graph of that region. Don't try to do it all in your head, because it's going to be very, very complicated. Finally, how do we choose a method to find a solid of revolution? We've seen three methods: the method of disks, the method of washers, and the method of cylindrical shells. So which one are we going to use? Well, here is one sort of strategy that I find quite simple, basic, and easy to implement. So this is how we're going to do it. First of all, let's work with preferably y as a function of x. Let's try to stay away from x being a function of y. If you have that kind of situation, we're going to simply switch the two variables. Okay, so switch variables if you're given the information as x being a function of y. Okay. Then use disk's method if the axis is horizontal and part of the boundary, okay, because that's what you're going to get once you rotate the region around the axis, a whole bunch of disks. On the other hand, use washers if the axis is still horizontal and separate from the region, so that when you rotate, what you get as you rotate is a bunch of washers. And finally, use shells if you're rotating around a vertical axis. Now, sometimes when you do this, in fact, it turns out that the integrals end up being very complicated and different to unravel. In that situation, it may be useful, just saying may be useful, okay, to switch the variable. So what I said earlier, switch if you're given as x equal function of y. Sometimes it may be useful to switch x and y when, in fact, you start with your y equals function of x and you end up with a mess. So in that situation, it may be worthwhile try to switch x and y and see what you get by reflecting the region around the diagonal line, and see if you end up with an easier setup for your integral. In some situations, however, this does not help at all, and so you just have to be happy with having set up the integral and maybe just have to wonder how to compute it.